A set of fast, polarized radio bursts has been uncovered inside more than a year of low-frequency array data. These signals lasted only minutes and disappeared before standard surveys could detect them. When the data were rebuilt to highlight rapid changes instead of long averages, the events came into view. Several nearby stars were producing radio bursts that matched magnetic patterns seen in our own solar system, particularly around Jupiter. Low-frequency radio waves carry information about magnetic fields and energetic electrons. They reveal activity that normal starlight cannot show. The problem is that traditional radio astronomy smooths data over long periods to create static images. Any short burst is erased in that process. The new method used in this study monitored nearly 200,000 locations across the sky and focused on sudden changes in circularly polarized radio waves. Circular polarization is strongly linked to magnetic activity. With this approach, the team detected signals that older surveys had filtered out. 27 bursts from 25 stars stood out clearly. Some of the stars were known to be magnetically active, while others had no radio detections on record. These bursts were compact and intense. Many lasted between 30 and 90 minutes. One lasted only 2 minutes but shifted in frequency as conditions around the star changed. Each event revealed how dynamic these nearby systems can be when viewed at the right timescale. Several bursts displayed familiar curved shapes when plotted in time and frequency. These shapes matched the arcs produced when Jupiter interacts with Io. In that system, electrons move through Jupiter's magnetic field and create narrow beams of radio emission. As the magnetic field rotates, the beam sweeps past Earth and forms a distinctive arc pattern. Seeing nearly identical patterns from stars suggests that some of them have organized magnetic structures producing the same type of behavior. One of the clearest examples came from the nearby star GJ 687. A burst lasting about 45 minutes reached up to roughly 160 megahertz and showed a narrow leg of emission with a sharp upper edge. The structure lined up with the Jupiter Io template almost exactly. This made it unlikely that the burst was random activity inside the star. It suggested that the emission came from a controlled magnetic region in motion. GJ 687 has a Neptune-sized planet in a close orbit. That planet travels through a strong magnetic environment. The research team calculated the amount of radio power expected from an interaction between the star and the planet. The predicted values closely matched the observed burst. Even if the planet has only a weak magnetic field, the interaction would still produce radio energy at the levels recorded. This does not confirm that the planet triggered the burst, but it shows that the explanation fits the available data without needing unusual conditions. Other stars in the survey produced structured bursts as well. Some are known for strong magnetic activity, so the events likely came from the stars themselves. Even so, the presence of organized arcs and clear frequency cutoffs shows that their magnetic fields are far more complex and active than standard imaging indicates. These bursts reveal fine structure that long exposures wash away. The key point is that these signals were present all along. They were simply hidden by the way radio data have been processed for decades. When the data are sliced into short intervals, the bursts appear instantly. This study demonstrates that many more events are sitting inside archived observations and can be uncovered with the same method. It also provides a new way to study planets that orbit close to their stars. When a planet moves through a magnetic field, it can trigger radio emission that reaches Earth. Detecting that emission gives insights into the magnetic conditions around both the star and the planet. The results show that the low-frequency radio sky is far more active than earlier surveys suggested. Stars near Earth produce fast, polarized bursts that reveal their magnetic behavior with surprising clarity. Some of these bursts resemble well-understood signals from the solar system, while others reveal new patterns that have not been studied at these frequencies before. With more data processed in this way, astronomers will be able to trace the magnetic interactions within nearby star systems and identify signatures that may point to the presence of orbiting planets.